Jussi Behrndt from Graz, and he was big on spectral theory for Dirac operators with singular potentials.
It's on geometric spectral theory. You see, so uh, I'm I'm certainly working in spectral theory. I'm quite sure about that. Maybe applications as well. Geometric, I'm not so sure. Yeah? So maybe this invitation was an accident. But after all, I found a result which has some geometric flavor. It will appear in the very end of the talk. Yeah? So I'm trying to satisfy all requirements to speak here.
Okay, and we're not dogmatic here.
Okay, thank you so much. Yeah? So let's see if you like it or not. Okay, so there's a lot of co-authors which I will not introduce here. It just reflects that this is not based just on one particular paper, but it's a little bit of an overview of things we've been doing concerning singular potentials. And this talk is focusing on Dirac operators, although I will also speak a little bit about Schrödinger. And so we will meet some of the guys from Jens' talk yesterday in this talk again. Okay, let's see if this works. No. Ah, yes, it does. Okay, so let me first introduce our, let's say, starting objects, which is Dirac operators in 2 and 3 space dimension. Here is the 2-dimensional version of it. So I'm not going into physics, but I give you the mass definition right away. So 2D Dirac is a vector-valued first-order operator. It acts in L2, but it's a vector-valued operator, so it formally acts in like 2 copies of L2. All functions here are kind of 2 vectors. It's defined on a first-order Sobolev space. Here I'm looking at the case that our operator is defined on the full Euclidean space. And so its action is basically gradient, first order. And then there are some objects which I'm recalling here, although they do not play an essential role for this talk. So the sigma j's are the so-called Pauli spin matrices. They are 2x2 matrices, and you multiply partial derivatives d1 and d2 by these matrices. Then m stands for the mass of the particle. It's typically non-negative. For mass purposes, it could also be a negative m, but it doesn't really matter much. So this is 2D Dirac, and there is a 3D copy of it, which looks very, very similar. It's again a vector-valued operator, but now it acts on 4 component vectors. So it's an operator in L2 with C4 valued functions, if you wish. The counterpart of the Pauli spin matrices in the 2D case are the so-called Dirac matrices. So they are 4x4 matrices, and they are composed using these Pauli spin matrices here. Beta is another 4x4 diagonal matrix, and it is just 1, 1, minus 1, minus 1. Again, this comes from physics. These matrices satisfy certain anti-commutation relations, which they need to do for Dirac's derivation, but all this will not play any essential role. So both operators have kind of natural domains of definition. H1 is first-order Sobolev space, which you require in order to have well-defined weak derivatives. Okay, so the first thing you check, and this is nothing essential, but of course it needs to be verified. So both 2D and 3D Dirac are actually self-adjoint operators. Self-adjoint always in the physical Hilbert space, right? So they act in L2, and they are densely defined, and well, they turn out to be self-adjoint. This is a kind of Fourier transform exercise, basically. And along this exercise, you also observe how their spectra look like. So this is an unbounded domain, R2, R3, so you expect some continuous spectrum, and this you can just read off by doing Fourier transform, basically. And so the essential thing here which makes theory for Dirac more difficult is these operators are not semi-bounded. So you have kind of 2 strips of continuous spectrum. There is a gap around 0. Okay, formally the gap could close. Yeah? If m is 0, then it's obviously the full real line. But otherwise, it's a symmetric gap around 0, and this spectrum is purely continuous. It turns even out to be absolutely continuous. But let's say the difficult thing here for further analysis is that actually it's not semi-bounded, obviously. So what makes life difficult in the non-semi-bounded case? Let's say all these variational principles, min, max, all this stuff is not available in the usual way as you would use this for Schrödinger. So this is, let's say, the key difficulty when doing analysis for Dirac operators. Good. So our unperturbed objects, and now let me first recall, let's say, some classical spectral theory for Dirac. This has mostly been done in the 3D case. You could check this monograph for further references and more physics behind these operators and equations. Bernd Thaler, he's actually from Graz. But he's from the other university. You see, Graz has two universities. Technische, where I am. Thaler is at the University of Graz, but if you check his publication record, he did publications in mathematical physics in the 90s. He wrote this book, which I think is very well known and the standard reference for Dirac. But then he changed his topic. And I think since that he started doing education, mass education, and he contributed in many ways in this direction. But he stopped with Dirac. So on the top of his career with this monograph, which is really well known, he changed the field. Okay, anyway. So this is the standard reference in this context. But now let's go further into spectral theory. And it's more like the 3D case has received more attention than the 2D case. Although what I'm showing you now, there also exist analogs in 2D. So this is just a warm-up. So you perturb. Of course, you perturb. You perturb by matrix functions. So the perturbation here is V. If it's in 3D, it's a 4-component vector, so you perturb by 4x4 matrices. This matrix could be non-symmetric if you wish, but of course, typically, people are interested in the case of symmetric or self-adjoint perturbations. Actually, most of the results actually concern perturbations which have diagonal form. And the physically most relevant case is that there is a kind of electric potential which is just a diagonal sitting on each entry the same function VEL, which is the real valued function in 3 variables. Then for physical reasons, one also perturbs with so-called Lorentz scalar potentials. They are also in diagonal form. Mathematically, it doesn't make any difference, of course. But for physical reasons, you sometimes distinguish the electric and the scalar potential term. Okay, so what is known in the most, let's say, classical case? So Coulomb is, of course, the case which, from point of view of mass physics, is the most relevant. So if your potential is radially symmetric, Coulomb type, it, of course, fits in this electric potential case. You need to be a little careful here with the nominator. So the nu corresponds to the atomic number. And what I'm showing you now is only valid as long as nu is less than square root 3/2. So what's true now? In such a case, V is actually a relative compact perturbation of the free Dirac, 3D. So you can just add in traditional way. The domain doesn't change. So you can work on the same operator domain as you do with the unperturbed one, and you end up with a self-adjoint operator. And also its spectrum is well understood, of course, because it's a form compact perturbation. The essential spectrum remains invariant. And so same situation as for the free Dirac. And now, of course, you ask what is going on in the gap. So in the gap, you have eigenvalues of finite multiplicity. And in this case, the eigenvalues actually accumulate to the thresholds of the essential spectrum. So you have a set of eigenvalues accumulating to m and minus m. And the situation is similar in the 2D case, which I'm not repeating. It's slightly different, but basically of similar nature. And of course, you can also see this is very classic. It goes at least back to Cato. And then it was further improved. You can go a little bit beyond this constant, but then you change the operator domains. And from a certain nu onwards, you cannot define a self-adjoint Dirac operator in a unique way.
The square root 3/2 means it's only one proton?
No, you see, it's the atomic number, which I think cannot exceed 137 or something. Yeah? Of course, you don't see any 137 because all physical units are made 1. And if you make all physical units 1, this number 130, I think it's 137 or 139 that you need for stability of the nuclei. It's 137. So if you make all constants 1, 137 turns into this. Good. Okay, once again. So this is very classical, and it just serves like a little warm-up. Yeah? What is going on in the Dirac case? Okay, so this talk is focusing on singular potentials. And the idea is it comes somewhat, it is application driven from graphene and other possible applications. And the principal idea is how you look at that type of potentials is the following. Suppose that your electric or even additional Lorentz scalar potential is kind of localized. Very roughly, I mean by that, you have large values in the neighborhood of a certain set and small values outside of this certain set. So the certain set here is supposed to be a curve in 2D, or it's a hypersurface in 3D. And now the idea is to replace such a type of localized potential by a distribution. So this is the best I could do with LaTeX in terms of pictures. So look at that from here to here.
Is there an actual convergence of spectrum in this?
This is a very good question, of course. This is what one asks. The answer is yes, but for Dirac, you have to be very careful. So this is the objective of the talk. Do spectral theory for Dirac operators, having in mind strongly localized potentials, and as a model, use singular potentials, which means delta distributions. Okay, so this is my plan. So before we actually turn to Dirac, let me do some warm-up. So the warm-up concerns Schrödinger. Of course, you can do singular perturbations of the Schrödinger operator as well. And this has been done much, much more than the Dirac case. And to familiarize you a little bit how you treat singular potentials, I will talk a little bit about Schrödinger. Okay, and there is more of, you see this is a 1,000 shilling banknote where the Austrians put Schrödinger. And I felt I should show it. 1,000 shilling is 80 pounds, something like that, 80, 85. It was the largest banknote in Austria, which also shows how proud we are of him. And okay, because Jens talked about it yesterday, let me add a little bit to it. So 100 years of quantum mechanics. So Schrödinger found his, let's say, popular and well-known equation in Arosa, Switzerland, in his winter holidays. At that time, he was professor at the University of Zurich. And he was there with some beloved, and her identity has never been clarified. So he was married, but they had a rather liberal life. And his plan originally was to go skiing. But then he got more and more involved. And I think in these holidays, he did not do a single skiing trip, but he was just computing. What happened with his beloved, nobody knows. And this is just a quote from a letter he wrote to a friend in Vienna. There is an English translation below, but in German you see it is kind of, it kind of reflects a little bit how he's feeling. Im Augenblick plagt mich. Plagen means like it's kind of painful to derive this theory. Right now it's not just I'm preoccupied, he's really having a hard time developing it. It's a bit painful. Of course, what I like is if I only were better at mathematics. So he's kind of optimistic and well, looking forward, and it will be very nice in the end. Okay, so this is a nice quote. So he wrote it to his friend, I forgot the name, some friend in Vienna. And if you want to learn more about Schrödinger, there's a nice video on the website of the University of Zurich. They produced it on a very professional level for the centenary in quantum mechanics. So it's like a 20-minute video which tells about Schrödinger and his life in these times and his work on quantum mechanics in the Swiss Alps. Okay, Good. So let's get back to mathematics, delta interactions, and this is somehow the most simple and easiest case, but it tells you a lot. So how you define a differential operator with the delta interaction. And this is in one dimension to keep it simple. So I'm just looking at Laplacian in 1D, second derivative, and I wonder how to define Laplacian plus distribution. So delta is the usual distribution supported at some point y. Omega in front of it is some weight factor, if you wish, which need to be real. And so you ask how you assign a mathematically rigorous differential operator to this kind of formal expression. So here's one way how you can do it. Your operator actually is just the Laplacian. You don't see the distribution in the action of the operator, but you see something unusual happening in the domain of the operator. And the unusual thing that happens concerns the behavior of the functions at the point y, where the distribution is supported. So I'm requiring psi to be Sobolev space H2 as usual, but just outside this point where something's going on. So in that particular point, there is still a continuity condition, as you can see. But what is really unusual is the derivative has a jump. And so this jump is proportionate to the value of the function. And so the idea is use this as a definition. Let us see if it works. So it works in the sense that this is a well-defined self-adjoint unbounded operator. It also works in the sense that if you formally put omega equals 0, so if omega is 0, you see the second condition becomes continuity of the derivative. And then you are back with the usual Laplacian. So then psi and psi prime are both continuous. This becomes H2, and everything is all right. If the omega is non-zero, you do a little change, basically, in the domain of the free Laplacian. And this little change is just a rank 1 perturbation. Rank 1 because you kind of put one condition in the domain. Rank 1 in terms of difference of resolvents, I should say. But it's a small perturbation, at least in terms of dimension. Not much can happen. And in fact, not much is happening. So if you perturb the free Laplacian, then of course the continuous spectrum remains the same. It's a rank 1 perturbation. And then you can just compute. If this omega is negative, there appears one negative eigenvalue located at minus omega squared over 4. Otherwise, the operator is non-negative.
Is it still the case that there's no embedded eigenvalue?
No, nothing like that. Yeah, okay, this is a good point. Could happen. Of course, in essential spectrum is not excluded. Right. But no, it won't happen in this case. So there's just basically one eigenvalue jumping out of the threshold, so out of 0, going down in case omega is negative. Okay, so another way how you find it in many textbooks to introduce this operators via quadratic form methods. So here's the corresponding quadratic form, which is the gradient or the first derivative taking care of the Laplacian. And this boundary term here gives rise to the delta, basically. And so this omega up here is, this operator up here is just the one representing this form. This would be another way to approach the whole thing. Okay, now I did not kind of convince you that this is really taking care of delta. It's an operator which makes sense in terms of spectrum and self-adjointness, but why is it reflecting delta? So here's a physics type argument. So let's look once more at this operator domain and pretend we are physicists for a moment. So imagine you have an eigenfunction corresponding to the formal Schrödinger equation here, corresponding to energy E. So it means we have solved this equation. And we just integrate in a small neighborhood around y, where the distribution is supported. So this is exactly the same thing, adding integrals. And now you compute. So the integral on the left gives you the antiderivative, gives you the derivative of psi evaluated at the endpoints. The integral in the middle, where the distribution is located, should give you the value of psi at the corresponding point y. On the right-hand side, nothing has happened. Now, let's suppose psi is continuous, and you send epsilon to 0, and you see then this second last formula in the limit just gives you this transmission condition you had in the operator domain. Yeah? So this is not a rigorous proof. This is more like a hand-waving proof. Yeah? I would say physicist proof without insulting anybody. Yeah? But it should be convincing you that this transmission condition is what an eigenfunction should feel at that point y where the distribution is supported. Okay, simple situation. So here is a situation for Schrödinger which goes a little bit beyond. Suppose your delta distribution is now supported on some hypersurface, n-dimensional space. Hypersurface, suppose it's kind of bounded, and we try to follow the same approach as we did in the 1D case for a hypersurface. So here is some notation, and I went to this lecture hall in advance to draw a pic. So the idea is basically we split the Euclidean space in two parts. There's a bounded part, omega interior. There's a complement exterior domain, omega e, and the boundary which separates these two domains will be denoted by sigma. And for this sigma here, we assume it is C2. Sometimes you can relax C2, but sometimes we will even make it C infinity. And functions in the following we will write just as two component vectors. Huh? So two components meaning that a function defined on the Euclidean space has a component which I obtain if I project to omega I, and there is another one to omega e, and then I'm just thinking of such a two vector. This is, I think, basically what I'm saying. Okay, so now we follow the same game as we did for the 1D perturbation in multi-dimension. So the goal is to define an operator that kind of reflects Laplacian plus delta distribution on the surface. Omega, which is this weight factor, can be, let's say, a constant. It can be an L infinity function. It should be real to keep things symmetric. Anyway, so it's more or less the same thing. Our operator is just acting like minus Laplacian. And then all this distributional stuff goes in the domain. So there's a continuity condition, which we had in the 1D case. Here it is now traces of Sobolev functions that coincide in H1. And then we have a jump in the derivative. There is a change of sign now, because it's a normal. I'm using the same normal. Yeah? You could use different normals, then it comes with the minus sign. But basically, it's telling the same thing. Yeah? The Neumann trace has a jump, which is proportional to the trace of the function. Okay, then there are some regularity issues. Yeah. You see, if I would make the omega a constant or a smooth function, then H2 is fine. But if the omega, which is acting on the surface, is rough in the sense that it's just L infinity, then you cannot go beyond this 3 half. But to be honest, this is more like it's technical stuff. You may think of H2, yeah? But then omega needs to be a little better. It doesn't matter in the effects I'm showing you now. It's parallel to what we did in the 1D case, up to technical issues. And so also it works almost the same way. Huh? So this gives you a self-adjoint operator, of course. This is the first thing you need to check. Again, if omega becomes 0, then you have continuity in the derivative. You get proper regularity, and you end up with Laplacian on H2. Spectrum, of course, as usual. But if it comes to perturbations, it's now different. You do not expect that this is something like finite rank or small or whatsoever, because you are changing the domain, the functions on a hypersurface. So this cannot be a rank n change or something like that. But you can prove it's actually a compact perturbation in terms of resolvent difference, of course. Yeah? So I'm comparing the resolvents of the unperturbed Laplacian and this one with the distribution. So the first thing I'm saying is it is compact, but it is actually better. So SP stands for Schatten von Neumann ideals. Yeah? So this is compact operators where, let's say, eigenvalues are LP. And so here the summability is directly connected with the dimension of the hypersurface. So n minus 1 is our dimension over 3. And in this game, it is usually, all these ideals are contained in each other. Yeah? So you want the p small, basically. The smaller the p, the more happy you are. Okay, but of course, there's a natural end here. Anyway, compact perturbations preserve essential spectrum. This is clear. And well, you could have accumulation of eigenvalues here to 0, but this can be excluded too. So in such a case, there's just finitely many negative eigenvalues, discrete. Now let's look once more at this perturbation. What people in scattering theory know by intuition is that higher type of powers of perturbations make things smoother. So what you expect is when you do not compare resolvents, but powers of resolvents, then this P class becomes better in the sense that it becomes smaller.
So in the situation where you would take omega to be a constant rather than do you get better Schatten class for? No, this is also for constant.
No, this won't help. What is behind this embedding theorems on the Sobolev spaces on the surface? Yeah? So this won't change. But you can go for higher powers. And this I'm still showing you because it is in certain interest in scattering theory. So if you go to higher powers, then the power appears in the denominator. And for scattering theory, this is nice because now you can make k sufficiently big such that p equals 1 satisfies this inequality. So if k is sufficiently big, this is trace class, yeah? Or nuclear, as you wish. And this allows you, let's say, to perform, let's say, a meaningful scattering theory in the sense that you have wave operators and AC parts of operators are equivalent and stuff like that. Yeah? Which leads too far for this talk. Yeah? So this was just a short intermezzo. I'm kind of telling you about Schrödinger with delta. And I have one more result, and it concerns somehow the question you asked for Dirac. What about approximation? So the question is, I'm having, whoops, now I lost this device. Oh, this is bad. So I'm having a Schrödinger operator with a delta distribution as a potential. Can I approximate it by Schrödinger operators with classical potentials, where the family of potentials kinds of shrinks and converges towards delta? So this is what this result here is about. Suppose there is a little epsilon tubular neighborhood of your hypersurface, and fix some L infinity function for simplicity, which is, let's say, supported in such a tubular neighborhood. Now you start rescaling it. So this rescaling just does the following. It makes the W kind of, its support shrinks, and its values grow. Yeah? But still, each of the W's, of course, it remains an L infinity function, yeah? if epsilon is positive. Well, then you can integrate this W perpendicular to your hypersurface. That would give you a little coefficient omega, which is L infinity. You can prove that. And now the theorem, without going too much into detail, tells you the following. I look at the classical Schrödinger operators with a family of shrinking potentials, omega epsilon. With these operators, I have no issues in terms of self-adjointness or something. They are just self-adjoint on H2. Any of these W epsilon is a bounded perturbation. It's L infinity. So these are all well-defined Schrödinger operators. And now one verifies actually that if you define this weight in front of the distribution as I did, you have norm-resolved convergence of this operator family to the one with the distribution. And so why are you happy about norm-resolvent convergence? Of course, it gives you full control on convergence of spectra. Okay, so this is the standard result. It's well known. Here it is in a certain generality, but this goes back to 70s, 80s. Yeah.
Are there results when instead of hypersurface, it's a higher dimension?
Now then life is much more difficult. There are, let's say, you see it already starts to define the operator if you consider delta on a curve in 3D, for example, which is the case which is treated best. There you already need some kind of regularization to define the operators. And I guess there are approximation results for this case, but I would not know a literature reference for it. Exner would know. Probably he has it in some of his papers somewhere. I guess it has been treated, but right now I don't. Okay, so there's an infinite list of references. The best known thing here is this monograph by Albeverio, Geshtesi, Krohn, and Holden on solvable models in quantum mechanics. They do point interactions, but point interactions in large detail. So this is the standard textbook, let's say. And many contributors that I talked about here is recent work, or not so recent, 10, 15 years ago by us. But actually the aim of the talk was not to speak about Schrödinger. I just did it to familiarize you a little bit with the delta, because the delta interaction for Schrödinger is kind of easier to understand than for Dirac. Okay, so here we see the next fellow from Jens' talk yesterday, Paul Dirac, who then received the Nobel Prize with Schrödinger 33. And we are now looking at Dirac operators, and we perturb them by delta singular potentials. So this is only repetition. You saw that on my first slide. 2D Dirac operator is a vector-valued operator. First order, it's self-adjoint, and okay, I'm repeating myself, but it's unbounded from below, and this makes life different to the Schrödinger case. Now the goal is perturb this operator by a distribution. And in this first result, my sigma that you can see here, now in the 2D case, I'm assuming it's a C infinity smooth curve. Compact C infinity loop. Okay, so the goal is to define now a formal, or to define a rigorous differential operator reflecting this expression. So the delta distribution is sitting on this loop, and in front there are some coefficients, and these two numbers, eta and tau, which are on the diagonal, they kind of represent electric and Lorentz scalar potential parts. Mathematically, you could just put one number. For certain reasons, there is two, and we will also see what happens if we play with the two. Anyway, so I would like to define a rigorous, well-working operator taking care of this formal expression. We are on a C infinity smooth case, and I'm using the same notation I had on the board and before. So here's the definition. And this is why I showed you Schrödinger first, because Dirac looks more complicated. In the end, it isn't. So the philosophy is the same. You see, the action of the operator is the same. You don't see any distribution here. But now something's going on in the domain. And maybe we just look at the main issues here. So here's the difference of the traces on the loop. So you are kind of measuring the difference, and you somehow compare with the average. And then these matrices, Pauli spin matrices, the normal vector, and eta and tau, and so on, they end up in this transmission condition. This is just to make sure it's a well-defined operator, but the essential condition is this, let's say, comparison of jump and average of traces on the loop. And you have to do it this way because you can check integration by parts, basically tells you this is the right type of transmission condition you need. But you don't see it immediately. It requires some computation. Anyway, this is the condition which makes sense. And now let's look at the operators, what these can do.
I have a very naive question. Is it coming from the formula, or because you impose that you want?
It is from both. It's from both. Mainly from the formula, you start integrating, wondering how a distribution should act on a smooth function. You split up integrals, you play, and then you see this must be a kind of transmission condition which makes things meaningful. Okay, so how about the spectra of such operators? So we distinguish in two cases, and now I think it gets interesting. So for some reason, suppose that eta and tau satisfy the condition. They are just real numbers for simplicity. This case we call non-critical because everything is how it should be. So first of all, this operator you just saw is self-adjoint. Not much is happening in terms of spectra or essential spectra because you perturb on a compact loop. So the continuous spectrum or essential spectrum remains the same. There appear a number of eigenvalues in the gap, but just finitely many. And also you have natural regularity in the operator domain. Yeah? Outside of the loop, everything is H1. Up to the loop, this is what you would expect. So the non-critical case is something not too surprising. This is what it should be. So it's even more surprising that then there is a different case. Now, if eta squared minus tau squared is equal to 4, whatever it means, you see what then happens is you have to modify the regularity and then the operator remains self-adjoint. But what is surprising to us is the essential spectrum changes. And in the gap, there appears an additional point in the essential spectrum. There is more. Also, the regularity of the domain changes. So there is no Sobolev regularity of positive order up to this loop. Locally, when you are off from the loop, of course, H1. But you cannot go to the loop and remain H1 or HS with any positive S. And if you make it smoother, you are just essentially self-adjoint. But the main observation here is this new additional point that appears. And now let me recall. I'm using essential spectrum here all the time, but what it actually means. So if you have a point in the essential spectrum of a self-adjoint operator, it by definition is saying that there is a lot of spectrum in a neighborhood. So if you look at spectral projections to any open interval around that point, their rank is infinite. So in other words, there are kind of two options. The easy option is you have an infinite dimensional eigenvalue. This may happen. The other option is this point is an accumulation point of spectrum. It could lie, of course, inside the continuous spectrum, but it could also be an accumulation point of eigenvalues, of discrete eigenvalues, without itself being an eigenvalue. Now you see this guy is actually inside the gap, so it is not embedded. Well, what can we say about that point? So first of all, you can play with these parameters. They just need to satisfy this criticality condition, and you can hit any point in the gap. We are looking here at one loop. If you take a number of loops, you can take more parameters, you can do more points. And now there's a recent paper by Italians. They started looking at it for a solvable case. So they assume that our loop is a circle. So what is surprising is, in the case of a circle, where you have some symmetry, you would actually more expect like this additional point is an eigenvalue, but they prove it isn't. So in the case of a circle, this new point in the essential spectrum must be an accumulation point of discrete eigenvalues. And so by definition, it then belongs to the continuous spectrum. Funny observations. So these are three young guys from Milan. They started computing. And well, we do not know what is happening, but it's an effect you prove. Okay, so here's a little more. Now the effects change somewhat because I'm now looking on a delta perturbation which is not sitting on a compact loop, but on an infinite ray. And for simplicity, this infinite ray is just the real line. So now I have a delta distribution supported on the real line, and I perturb my 2D Dirac by such a delta. Then you get the following result, which I'm not going to discuss. So there is no tau here for simplicity. There's just an eta. And then you end up in a critical case if eta is either -2 or eta is 2, because in that case, eta squared would be 4. So here you see how the spectrum changes when the eta changes. And I have a postdoc in my group, and he did a video. And I think I'll show you the video, which says basically, well, the video says what the theorem says, but it's a bit more convenient to watch a movie than looking at all these quantities. Okay, let's see. I had difficulties in the morning to play it, but let's see if it works now. Or sometimes people say I should clean up my desktop.
Very easy, I can do it for you.
So here's the video. So look, the eta is running. It goes from -10 to 10. So continuous spectrum changes, but then if eta approaches the critical case, it disappears. And now if the eta continues to grow, you see, the continuous spectrum again moves. If eta is 0, it's free Dirac. So you have the gap. Now eta moves ahead. And again, you see the same thing. Eta is growing, continuous spectrum is changing continuously, which is fine. But then when you approach the critical value, there's a transition. And it is this one. Yeah? Continuous spectrum disappearing. This is kind of surprising. Yeah? Or power, it comes back. Yeah? And again, the eta is running. And once eta is 10 or something, you enter with it. So the effect is not that the continuous spectrum is changing. This is clear if you perturb on an unbounded surface or unbounded curve. But the main effect is here that there is a transition in the sense that spectrum is really disappearing or appearing out of nowhere. Good. So this was the video that Peter made for me. Okay, we go back here. Okay, so you just saw this theorem in real life. Huh? Here's Peter's video, which doesn't work because I got a new laptop and I had some software problem. Anyway, 3D Dirac, and I'm now going a little faster because time is running and I want to show you a few things which also lead to geometry type results. So here's 3D Dirac. We saw that in the very beginning, self-adjoint, unbounded operator from above, from below. And we perturb 3D Dirac by a delta distribution supported on a hypersurface. Yeah? Now the surface for the beginning is C2, and the approach is basically the same we had before. Yeah? Sure.
M is a constant, right?
Yeah, it's the mass of the particle,
And
which is
beta,
non-negative.
what is beta? This is the force.
Eta, tau are just real numbers.
No. Beta.
Beta. Beta is a 4x4 matrix which is diagonal. 1, 1, minus 1, minus 1. It's the force of the Dirac matrices, if you wish, yeah? Which is not called alpha 4, but it is called beta. This is no, they will. No, this is not. No. Oh, right. Thala will come and. Okay, so let's move ahead. So it's basically the same type of transmission condition in 3D as we had in 2D. I'm not talking about that. There's a non-critical case where again things are as you expect. Continuous spectrum remains invariant, finitely many eigenvalues in the gap. If you wish, you can play with etas and taus to keep the gap empty. This is just a But then there's a critical case. Critical case, self-adjointness is a problem, but can be ensured. Of course, the infinite rates will remain in this. This is what you expect. Regularity is an issue, and you do not have H1 or any positive Sobolev regularity up to the surface. Essential self-adjointness if you restrict to some more smooth space. And here's now the first observation, which this was a couple of years ago. So if the sigma is smooth and it contains a flat part, I think it's clear what I mean by flat part. Huh? Then at least we were able to show that again this point, minus tau over eta times m, appears in the essential spectrum. But of course, this is only a partial result because this is just an inclusion. We don't know. Huh? So it took a while until Ben Hillan and Pankrashkin took over. Now comes the geometry part. Huh? So now wake up. So what do they do? Suppose your surface is C infinity. Let kappa 1 and kappa 2 be the principal curvatures. And then they kind of take the maximum of the difference. This gives you a non-negative quantity, k sigma. And now look what happens. This k sigma specifies the interval around that point minus tau over eta m, which we had before, that gives you an additional now strip in the essential spectrum. Okay, now you are geometers. When is this kappa sigma 0? It's 0 if the principal curvatures are the same. So this must be a sphere. Okay? So if it's a sphere, there's just a point, right? Because this is 0. And once you start changing the sphere, you of course end up with a positive k sigma. You blow up this point to an interval of essential spectrum. I found it great. it's a very nice result. The only bad thing about it is they proved it and not me.
Can I in your proof, how does the flat part enter the proof?
We define we construct a singular sequence. Yeah? And with this flat part, we can kind of cut off the sequence and play with it and show that it's a singular sequence corresponding to that spectral point. Their proof is very different, yeah? Using pseudo-differential techniques, and this is they reduce it to a result on pseudo-differential operators where they read off the spectrum from the principal symbol. Okay, yeah. So this is Ben Hilal Pankrashkin 24, and now I have still a few minutes to go. So, well, yeah, I was not involved, which okay, this is how it is. Yeah, sometimes people do better than you. Anyway, let's okay. So the story continues. So more recent developments, and the story continues now a little different, but it will have a happy end. This is the essential thing. This was the time where US presidents were interested in science. But the important guy is the one on the left. Yakir Aharonov is very much well known for the Aharonov-Bohm effect. So it's a vector potential in quantum mechanics, to make it short. And they found this effect in '59, or they published it with David Bohm. Of course, at that time, Yakir was a young guy. So this is in 2009. He's not that young anymore, but he's still alive. He's still active. So here's the next pic, which was taken 2 years ago in Cetraro, a nice grand hotel in the south of Calabria where they do conferences. The Italians know how to do it. Okay, so you see the editors of the Quantum Studies Journal. And so the second from the left, this is me. In the middle is Daniele Stroppa. He was president of Chapman University. Fabrizio Colombo, Andrew Jordan, a friend from Israel, and Yakir at the bottom. Yeah? So in 24, he's still alive, active physicist, and we've been collaborating on a different topic with Yakir. So I knew him, and it was nice to meet him again in Cetraro. Now, when you want to talk to him, he's very talkative, nice guy, yeah? in the middle of the 90s by now. When you want to talk to him, you need to smoke a cigar. Huh? Huh? So Yakir, I think he has a good living style, but so he is smoking cigars all the time. And the best way to talk to him is get yourself a cigar, sit and talk to him. So I did that, as you can see. And then he starts talking science. Yeah? Hey, what are you doing? What is your reason? What are you interested in? And so on. Okay. Well, I started talking about Dirac. Huh? Dirac, and we observe that there is additional spectrum. For the case of a loop, there's an additional point appearing in the gap, and for the case of a smooth surface, there's even an interval. And then it takes a while. Of course, he speaks a different language, or I speak a different language, before we start to understand ourselves. And then he says, but he's not surprised, because it's an infinite domain. Yeah? So his question is, will this happen if the particle is in a finite box? Okay, by finite box, he actually means take a domain where your surface or loop is contained in, and put self-adjoint boundary conditions on the outside of that domain. Now, of course, you are in a finite domain, so a physicist will not expect any continuum. No continuous spectrum, also, of course, in differential operators. Of course, there are counterexamples, but very roughly, by intuition, bounded domain, there is some Relic embedding result or something similar, gives you compact resolvent and discrete spectrum. So for bounded domains, will there be continuous or this essential spectrum effects that we observe in the unbounded case? I say to Yakir, yeah, of course, sure, of course. Yeah? Because we understand that these semi-infinite rays, they come from the unboundedness of the domain. But it's only in the critical case that this delta interaction gives you additional continuous or essential spectrum. But well, we started talking for a while, and then it became clear, okay, actually one should make it precise. And so here's the happy end. Yeah? I approached Ben Hilal and Pankrashkin. Why not start a joint project? And so we proved now in a recent paper, which is still not finished, unfortunately, that exactly this happens what we were expecting by intuition. It is clear. So if you have a bounded domain, you put a self-adjoint boundary condition, zigzag or MIT bag condition or whatsoever you use for the Dirac, yeah? But some meaningful self-adjoint boundary condition on the outer boundary, then of course the infinite rays of continuous spectrum disappear, sure. But what remains in the critical case is of course this additional point or the additional interval, which is, let's say, defined by the principal curvature differences of the smooth hypersurface. Okay. So now you can see I'm German. I'm exactly in time. 11:50. Thank you very much.
You mentioned that it has to do with the principal symbol. So is it equivalent in some sense similar to group J-Manar result, that it's a set of points where the principal symbol vanishes?
I think this is where it comes from. The spectral problem for Dirac, you reduce in some boundary integral formulation to some boundary integral operator. Now the integral operators first look kind of hard to treat and very complicated. And now you start to do many compact perturbations. And until these integral operators reduce to something constant. And now you use exactly this type of result. But this also, you see, all these compact perturbations and reduction to the boundary or surface, unfortunately, the price to pay is you lose very much control of what exactly is happening with the spectrum. We just know invariance of essential spectrum, but we have no idea, is it like accumulation of eigenvalues to that point, or is it continuous spectrum or isolated eigenvalue of infinite dimension or something like that. So it's kind of abstract perturbation theory on the one hand, reducing all the way down to some good pseudo-differential operator where you read off what is going on.
So you need a surface or a loop to be smooth, right?
This is the pseudo-differential methods. Although, honestly, I mean, our proof needs it, but this is not the reason for the effect.
When I dabbled in Dirac operators, we could get our results to work for potentials that were either this scalar, this thing, but also if they were scalar multiples of any of the Dirac matrices. Do you expect that you still get, they have to be one of those?
Yeah, you can build it in. They sometimes call this magnetic potential. You can build it in. I don't remember if there is a counterpart for the critical case if you have more like coefficients in front of the perturbation. For the situation that actually your delta is supported on a real line, this is all done via Fourier transform methods. And there I think also 3 or 4 parameters are allowed. It leads to even more spectral effects. Yeah? You just do not play with eta and tau, but you also have, I think, a lambda or an omega or something in it. And then there is more that happens. So I think for the case of delta on a real line in 2D, this has been done. 3D, I'm not so sure.
And just a question, following your remark, you don't know the nature of the spectrum. What if you consider potential sitting in a small neighborhood of sigma, but finite, and then rescale both the support and the size of the potential, so you do some sort of approximation?
Okay, this brings me back to the very first question. This approximation for Dirac in norm-resolvent sense works under certain restrictions. In the critical cases, it doesn't work. So in fact, we have some sharp estimates and results, and we use these critical cases as counterexamples that this cannot be extended. So this is not the way to do it. It won't work.
Do you look at dimension 2 and 3 only because of their physical relevance, or there's something that breaks? Or Dirac operator higher dimensions is very easy.
You could do it with the Clifford algebra and higher dimensions. We didn't, honestly. We didn't. It's not so much an effect of dimension.
Yeah, it didn't look like an effect of dimension, so I thought it should.
No, I believe by intuition that this goes beyond my expertise. You can do it in any other space dimension.
I think it would be interesting to see how in this situation the principal curvatures interact. Because I mean, you can have.
Yeah, of course, then you would have more. But as far as I know, or at least I have not seen any papers on Dirac with singular interactions in dimension 4 and higher.
Yeah, I mean, for some reason, for Schrödinger, people seem to think we can go any dimension and it's we don't care that these are not physical. But for Dirac, people really stop at 2 and 3, 4. And I don't know why that's the.
Generally speaking, life with Dirac is hard.
He'll tell you that 2 is also unphysical.
Well, I mean, I'm not a physicist, so I don't care whether it's physical or not.
Tim is also not, but he's very
No, but summarizing, I believe the methods we apply, they would allow also to do similar things in higher dimension. It is by no way restricted to do 3D. You need trace operators, estimates, and all this you would have in higher dimension.
Is there some physical explanation why the critical case is critical?
No. This is the question people always ask. I don't know.
And why is it critical?
Okay, we call it critical. Yeah, this is but okay. So why does it happen? Mathematical explanation is very simple. Certain operator loses Fredholm property. Yeah? Certain operator somewhere is Fredholm as long as you are non-critical, and in the critical case it loses Fredholm property, and this is what happens. But no physical explanation. Yeah? This is of course what I asked Jack here. Yeah? Can you explain? No, I cannot explain. No idea. It's a mathematical curiosity.